Welcome everyone. I'm Jan Pennekamp. I'm with RWTH Aachen University, and this is joint work with colleagues from KU Leuven. Today I'm going to talk about secure end-to-end sensing in supply chains. This work is part of a federal research-funded cluster in Germany, which has a goal to create a worldwide lab in the domain of production technology. There we want to utilize information from production development and use it to improve manufacturing overall. This also includes information sharing along supply chains. Here, the expectations are that business collaboration will increase the business performance significantly. However, the information sources where we retrieve our data from might be unreliable. Therefore, we consider the following scenario: sensing in untrusted environments. Here, we want to improve the tracking of products, crates, and containers, and offer condition monitoring if needed. For example, in food chains, verifying that the cold chain was not interrupted is a crucial aspect. Let's take a look at our scenario. For example, we have a product that's packed into a crate, and this crate is packaged into a container and then transported on a truck until the container reaches its destination. There, the crate is unpacked, repacked, and put onto another truck. Once this container reaches its recipient, the crate is unpacked, and finally the product is retrieved as well. As you can see, we can have a lot of interaction along the supply chain, and a lot of steps can go wrong. So currently we have a lack of guarantees in this situation because the data that we receive from these untrusted environments is really unreliable. We currently do not have any accountability. Information might be missing, incomplete, or inaccurate, and transmission can potentially be delayed even if they contain really relevant business information. Furthermore, the data processing and forwarding is completely untrusted. Research in the area of supply chains usually deals with the processing of data and not how to improve the sensing of information. Consequently, they usually assume that inserted information into the platform is accurate. Second area of research deals with the reliable identification of products. So for example, how to identify counterfeit products and to make sure that only authentic products are delivered. Our goal here is to make the information reliable even before it's processed by these approaches. Based on this situation, we coined the notion of secure end-to-end sensing, where we refer to the data flow from the sensor, so once the information is actually created until it reaches the intended recipient. In this scenario, we identify 4 requirements for trusted sensing. First, we have the tamper-proofness. So the sensing and processing must be untampered to allow for long-term guarantees along the complete supply chain. Second, we need authenticity. So we should only record original data, and we want to prevent false data ingestion. Third, we have the aspect of accountability because we want to introduce responsibility into the supply chain. Therefore, information must also be verifiable. And finally, our proposed solution must be applicable. This holds both in terms of an affordable solution and a scalable processing. Ideally, we can easily equip today's supply chains with our solution. Taking a look at the utilized building blocks, we have trusted execution environments on the one hand. They offer us isolation, so they can protect trusted applications from manipulations even in untrusted environments. Second, they offer attestation, so we can make all the computations verifiable by third parties and thus confirm the made sensing. Third, trusted execution environments can offer memory mapped input outputs that support exclusive sensor access from within the trusted execution environment. Thereby, the sensed information cannot be tampered with. Some famous examples of trusted execution environments would be Intel SGX, which is part of a lot of regular processors. Then there is ARM Trust Zone, which is, for example, commonly utilized on smartphones. And then there is COMSYS, which is a low-cost trusted execution environment developed by KU Leuven. On the other hand, we have blockchain technology, which offers us a tamper-proof lock with distributed consensus, even in environments with mutually distrustful participants. It allows us a storing of digital fingerprints in a tamper-proof manner. Now, moving on to the design overview. We want to establish a trustworthy data flow from sensors to storage. So first, we have the transportation unit that deals with the sensing. There we utilize trusted sensors that make use of trusted execution environments. This data can then be transmitted to a transmission gateway where it's aggregated and forwarded. The information then arrives at a trusted server, which also utilizes trusted execution environment and can attest the original sensed information. If no transmission gateway is used, the sensors can directly send their information to the trusted server. The trusted server then derives fingerprints and potentially public information and records this information on the immutable ledger. To account for more excessive storage needs, we can also store encrypted raw data at a dedicated storage provider. Some examples of which technology we want to utilize at the different processing steps would be COMSYS for the sensors to allow for cheap yet trustworthy sensing hardware, ARM Trust Zone for the transmission gateway that's part of the container, for example, and then Intel SGX for the trusted servers that are running in the cloud. With respect to the feasibility study that we conducted, we take a look at both the costs and the performance. So with respect to the costs, we can enable trusted sensing for already 10 euros. So this includes the sensor and the COMSYS node that's required to enable the trusted sensor. Here we can also account for use case specific additions. For example, include humidity sensors if needed. COMSYS can cost only 2 euros per piece, so all the other costs are for the sensing hardware. Performance-wise, COMSYS can process multiple readings per second and can run several months on battery. Overall, different types of input are supported there. Continuing with the transmission gateway, we can build such devices for 50 to 300 euros depending on the utilized trusted execution environment and the required performance. This can also include the communication overhead that's required to communicate with trusted sensors. For example, we can utilize 4G here or rely on other communication such as Wi-Fi or Bluetooth. As we said before, this is an optional component, as trusted sensors could also communicate with the trusted server directly. Here, for the performance, we require a single device per container, and it's used to reduce the transmissions to the trusted server from the trusted sensors. Such a gateway also helps to deal with phases where the container is offline or no network access is possible or supported. Then finally, for the trusted server, we can rely on regular cloud infrastructure that's available at comparable costs, at similar costs like regular devices without trusted execution environments. As we know, cloud computing offers us scalable performance if needed. Continuing with our security discussion, we have a number of security properties that we utilize in our design. So the trusted execution environments ensures authenticity of data, and the attestation enables verifiability of all recorded information. Furthermore, we can detect sensing gaps and make these issues also transparent, for example, by publishing the lack of sensed information on the blockchain. However, some attack vectors remain with respect to our proposed end-to-end sensing. Trusted execution environments are vulnerable in general. However, this is not an issue of our individual design and must be tackled separately. Secondly, we cannot exclude attacks on the sensors directly. For example, this refers to the physical tampering of the sensor or placing it in incorrect locations. For example, you could only put the sensor into a cooled compartment of the container and do not cool the remainder of the container. Similarly, incorrect usage of the sensors, so for example, associating the wrong sensor with a different container, are human-made issues there. And then third, which I already mentioned before, is that we need reliable product identification to make sure that products and goods that are sensed by our design are actually the products that we want to sense. Now, to conclude, we propose a design to enable trustworthy sensing along supply chains. Interactions in these untrusted scenarios are usually, or the data that's recorded in these interactions is usually unreliable and error prone. However, it's really desirable for companies to have this kind of information. Therefore, we propose a secure end-to-end sensing. We utilize trusted execution environments in hostile environments to make sure that the data is actually processed in an untampered manner. We further utilize a blockchain to record the fingerprints on an immutable log. Thereby, we enable accountability and verifiability of all sensed information. Our feasibility study shows that we can implement such a design with low costs and suitable performance. We can also account for use case specific scenarios where special sensors or condition monitoring is needed. This can also include live condition monitoring where values are submitted in real time. With this, I would like to conclude my talk and thank you for your attention.